Good morning everyone, and welcome to today's worked exam answer video. Today I'm having a look at what could be both an AS and an A-level question covering enthalpy of formation, Hess's law cycles and a calorimetry experiment where we are measuring the enthalpy change. So as always, you'll be very familiar with this by now. I'm going to go through and do my highlighting, do my worked answers, and then I'll be back to explain exactly how I have gone about writing said answers. See you in a minute. Okay, here we go. Part A, define the term standard enthalpy of formation. You have to learn this, and whilst there aren't many definition questions on an A-level paper, in an AS paper they are far more likely. So if you're sitting the AS in May, then 100% I would expect you to have learned this definition, the definition for standard enthalpy of combustion, the one for Hess's law, which is coming in the next part of the question, and I would say they're the three key ones from energetics. Also potentially mean bond enthalpies, so what we mean by bond enthalpy and then how they are worked out to be averages. Anyways, the standard enthalpy of formation is going to be worth 3 marks. The three key things are for saying that it is the enthalpy change when 1 mole of a compound, it's always 1 mole of the compound, is formed from its elements in their standard states for the second mark under standard conditions for the third. So this definition, not only is it really helpful to know for questions like this where you're getting 3 marks for literally recalling the definition, but also we are going to be in part B drawing a Hess's law cycle, and we have been given enthalpy of formation data. We now know that the values we have been given in the table are all for the formation of 1 mole of a compound, and you'll see why that's important in 1 second. So that's our definition there. In part B, we have to state Hess's law and use it together with the data given in the table below to calculate the standard enthalpy change for the following reaction. So we've got magnesium oxide reacting with hydrochloric acid or hydrogen chloride in the gas phase to form magnesium chloride and water. So first up, we need to know what Hess's law is, and Hess said that the enthalpy change is independent of the route taken and is only dependent on the initial and final states. What does that mean in slightly plainer English? It basically means it doesn't matter how many steps it takes us, so long as we start with the reactants and everything is the same about the reactants, and we finish at the products and everything is the same about the products. It doesn't matter whether we go the direct route or we go slightly around the houses. If we go slightly around the houses and we add those processes together, it will give us the same value as if we were to work out the process directly. So that's what it means by then applying Hess's law. We're basically saying in my little cycle, I'm going to go via this intermediate step, then I'm going to get to my products, and if I add those 2 steps together, it will be the same as the 1 step across the top. So we've got to understand how to construct cycles. Now we've been given enthalpy of formation data. So in an enthalpy of formation cycle, it's all about how we're forming the compounds up here. And as we've just learned in our definition, it's when 1 mole of these compounds are formed from the elements in their standard states. So what elements do we have in here? Well, we've got magnesium in its standard state as a solid. We've got oxygen, which is O2 as a diatomic gas, but we only have 1 oxygen atom, so half an O2. We've got hydrogen, which is diatomic and a gas in its standard state, and we've got chlorine, which again is diatomic and a gas in its standard state. So the elements will go at the bottom, and then our arrows are all going to point upwards because we are given in the table the energy that is released when 1 mole of magnesium oxide is formed. We're given the energy released when 1 mole of HCl in the gas phase is formed, and so on and so forth. Now, this 2 here, very important. We have the value for forming 1 mole of HCl. We're actually forming 2, so we have to multiply that value by 2, and I have labelled all of my arrows with the values from the table, and because the HCl is the only one where we've got more than 1 mole, that's the only one that I need to multiply here. The red highlighter arrows represent my Hess's law arrows, and whenever our Hess's law arrow goes against the arrow drawn on for the cycle, as it does in my reactants, it doesn't on the product side, the red arrows and the highlighter red are all in the same direction. When the Hess's law arrow goes in the opposite direction, we have to change the sign of the value. So in forming the compound, it releases 602 kilojoules per mole of energy. Going the other way, we're therefore going to need to input 602 kilojoules per mole of energy. So I've rewritten those two numbers as positives because those are the two arrows that go against the Hess's law arrow. And then Hess said we need to add those two steps together. So I'm going to add 602 to 2 lots of 92 to minus 642 and minus 286. And that gives me an answer for the enthalpy change for the top reaction between magnesium oxide and the hydrogen chloride of minus 142 kilojoules per mole. So an exothermic process. Cycles can be tricky. My key is you always base the cycle on the data that you were given. So we were given formation data, so the cycle looked like this with the elements at the bottom. The other type of data you might be given is combustion data, in which case you would have the products of complete combustion at the bottom. Why? Based on the definition, standard enthalpy of combustion is the enthalpy change when 1 mole of a substance is completely burned in oxygen. So that would suggest complete combustion. So it's always the data you are given that drives the type of cycle that you draw. Any questions on that? As I've always said, please just get in touch. And then finally, we were given what initially looked like quite a difficult calculation for 8 marks. However, when we break it down, I think it's actually a very generous 8 marks, and I think you could very easily not get 8 marks for a very similar question. So, in an experiment, so we're using the same reaction as above, we've got an excess of solid magnesium oxide and we're adding that to 50 centimetres cubed of 3 mole per decimetre cubed hydrochloric acid. The initial temperature of the solution was 21 degrees. After the reaction, the temperature had risen to 53. We're then given the specific heat capacity of water as 4.2 joules per Kelvin per gram. We have to use this information to calculate the enthalpy change for the reaction of 1 mole of magnesium oxide with the hydrochloric acid. Now the magnesium oxide is in excess, so we don't have information about that, but we do have information about the hydrochloric acid, and we can write a lovely balanced chemical equation and use our mole ratios, which is exactly what I've done and will explain. Then it says, for your calculation, you should assume that all the heat from the reaction is used to raise the temperature of 50 grams of water. Fab. So this is a Q is MC delta T question, and then we need to use a second equation where delta H, the enthalpy change, is worked out by doing Q, which is the heat change, divided by the number of moles that we actually reacted in our experiment, and that will give us the enthalpy change per mole. And because we're doing it for the magnesium oxide, I've written this lovely equation here. So we were told 50 centimetres cubed of 3 mole per decimetre cubed hydrochloric acid was used. So I've converted my volume into decimetres cubed, got my concentration. Moles is worked out by doing volume times concentration, or concentration times volume. Sorry, that threw me for a second, having them the other way round. And I've got the number of moles there as 0.15 moles. Now, the magnesium oxide was in excess, so we know that all of that hydrochloric acid is going to react. We can then work out how much of the excess of the magnesium oxide therefore reacted, because they are in a 1:2 ratio, so 1 for the magnesium oxide, 2 for the HCl. So I've divided my 0.15 moles by 2 to get 0.075. We're going to be using that in the second part of our calculation in a moment. Next up, we've got to get a value for Q. Q is equal to MC delta T, where M is the mass of the substance experiencing the temperature change, and we're told at the end that we should assume that all of the heat from the reaction is used to raise the temperature of 50 grams of water, so 50 grams. The specific heat capacity was given to us as 4.2. You may get it slightly more accurate than that at 4.18. but you will always be given the specific heat capacity. And then it's delta T, so change in temperature. It was 21 and it rose to 53. So it's the difference between 53 and 21, which is 32. Put that into your calculator and you should get a value for Q of 6,720 joules. Now, enthalpy changes are measured in kilojoules per mole, so having Q in joules is no good. So I've divided that by 1,000 now, get it out of the way as it were, so that gives us 6.720 kilojoules for the heat energy change. That is the heat energy change when 0.075 moles of magnesium oxide reacted, and we want to know the enthalpy change for 1 mole of magnesium oxide reacting. So this is where my moles are going to come in, and we're going to do the heat energy change divided by the moles to get us a value for delta H in kilojoules per mole. Now, that is not going to give me a negative answer on my calculator. All values for delta H calculated using this method will give us positive answers because Q will always be positive. Whatever the temperature change is, it will be quoted as a positive number. However, that does not mean that all reactions are endothermic. This one is exothermic. How do I know? Because it says after the reaction, the temperature had risen to 53 degrees. If the temperature is rising, that means heat is being released. And it also says later on, the reaction is used to raise the temperature of the water. If it is exothermic, you have to manually add the negative sign in front of your answer. And one of the 8 marks will be just for popping that negative sign in there. So you can do all the hard work and get the right number. If you forget your negative sign, you've lost a mark. If you think the reaction is endothermic, leave it positive. You don't need to do anything with that because the calculator will always give you a positive answer, and delta H values for endothermic reactions are positive. So that is my energetics enthalpy changes Hess's law question. As always, if anything has been unclear, please let me know. Any questions at all, again, please get in touch. Hope you have a really lovely day, guys. Thank you.